This will be exam 4 review. On chapters 23 through 25. All right, so that'll be exam. As far as that, so it's basically covering light, images, mirrors, and stuff. All right, so I'll go through this section. All right. So for the test, all right, I'll just go through each one. So for chapter 23, all right, first section will be on reflection, 23.2, reflection, plane mirror. All right, angle of incident equals angle of reflection. For that, as far as that is concerned, and then plane like a mirrors, and how that works. All right, I'm not going to do anything. We're skipping 23.3 on mirrors, per se. So we're not going to do anything on mirrors. Okay, 23.4 will be index refraction. All right, and 23.5. Basically, what do we mean by index refraction? What do you mean by that is, again, speed of light is 3 times 10 to the 8th meters per second, and N is given by C over what the speed is in the medium. So this is the speed inside the air, this is in air, and then the index refraction, where C is always greater than V, I should say greater, not a lot greater than V, so that's the index refraction. So N is always greater than or equal to 1. Okay, so that's that part there. Snell's law. Went through that, N1 sine theta 1 equals N2 sine theta 2, where again the angles are measured relative to the perpendicular, right, to the normal. And we refer to that as N1 is where we start, N2 is where you end up in, right? So that's Snell's law as far as that's concerned, right? So that's that part. 23.6, which is kind of a follow-up on this. This is like air to glass, but if we go the other way around from, say, glass, so total internal reflection when N1 is greater than N2, so like going from glass to air, water to air, or something like that, then the critical angle, which we went through, is given by sine theta critical is N2 over N1. Where again, this is where we're going from water to air or glass to air, and so this has to be less than or equal to 1 for this to work. Okay, So that's the parts related to refraction, right? 23, 4, 5, and 6. So I'll leave that up for a minute. Okay. All right. Moving on from there then, we have all right, 23, 7, and 8, and that's related to thin lenses and either convex or concave. Okay, F greater than 0, here F is less than 0, right? So that's what we're dealing with there. And related to that is the thin lens equation. 1 over P plus 1 over Q is equal to 1 over F, where we also call this the object distance, and we call this the image distance, all right? So I prefer to use P and Q because we don't have subscripts, but the book uses D sub O and D sub I, so object and image, and then the magnification is given by HI over HO, which is equal to D sub I over D sub O. All right, actually negative, but all right. So that's what we have there. We have lab 10 was related to this. Is also included lab 10 on lenses, as far as that's concerned. All right. And then last part, 23.9, we had combinations. All right, of lenses. And this was also related to the last part of lab 10, where we had 2 lenses together. How does that work? All right. And that is chapter 23. Okay. That's chapter 23. And I'll move on to chapter 24. Wave nature of light. And this is related to the fact that light is a wave. So the principle of diffraction we'll get into. We talked about light coming into a slit will spread out. So it has a wave nature to it, and go from there. So 24.3 is interference. We talked about that. So 2 points separated by distance D. The peaks on the other side this is the central one, right? Angle D sine theta is m lambda. m lambda, I should say, not n. M lambda, where this is m equals 0, m equals 1. Other side, m equals -1, and 2, and so on. So you get peaks based on this relationship. Okay? That is interference. Right. 24.4. Again, dispersion. Talked about that. For Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. The spectrum, so we have higher, let's say this might be 1.55 index refraction, 1.45, and we get the range. Oh, got these backwards. Generally, higher wavelength has higher index refraction. Shorter wavelength, higher energy has higher index refraction. Red has lower index refraction. So dispersion is the fact that and white light going into a prism will be broken up into the spectrum. Red is deflected less, and violet is refracted the most. Okay. And that's similar to the principle of rainbows. We talked about that as far as what goes on there. So rainbows, same kind of principle. So that's 24.4. 24.5 is diffraction. And again, diffraction is when you have the fact that light is a wave and it will make spread out just like a sound wave would do. And so we have diffraction. And the only thing we're going to be dealing with here is 24.6 is diffraction grating, which is actually used to measure light. And a diffraction grating is sine theta is m lambda over d, where d is the distance between each slit. So you have many slits together, and so you end up with dot, dot, dot. This would be sine theta, m equals 0, m equals 1, m equals 2. So d sine theta is m lambda. So for the first one, sine theta is lambda over d. So this is very much like interference pattern. So this is the formula. This is the general formula, and this is for the first dot we see when we had the laser, and you get the individual dots on each side, not this spread out pattern. That's 24.6, and yeah, and then this was also related to spectrometer. So 24.7 is the spectrometer. And this is related to the fact that you have light. Spectrums of color, this is based on the lab we had there. Right, and so you get the colors using the spectrometer, which uses a diffraction grating. So that's it there. And oh, and then the last section we're covering Okay. Then the last section, 2410, was polarization. All right, what do we mean by unpolarized light? Like sunlight. And what the polarized I is I naught cosine squared of the angle. All right, we talked about that. That's polar. So when you have different angles between sheets, the intensity of what comes out is related to the square of the angle between those two sheets of polarization. And then Polaroid sunglasses. Based on reflected light, which is polarized. All right, so reflected light is polarized, so taking advantage of that, you can use a Polaroid film to reduce glare but not make everything dark. And that is the end of lab. That's chapter 24. Okay. All right, the final section, final chapter I should say, is on chapter 25. Optical instruments. All right, and this is fairly straightforward. A little bit, it's useful to know what like 24 25.1 f-stop on a camera. All right, what does that mean? It means the size of the opening, so the way cameras work and the way focusing works. Okay, 25.2, human eye. Included nearsightedness, and farsightedness. Okay, what's the difference between the two and how you correct for both? We talked about that earlier, and the kind of lens for each one. All right, which one goes with which? So I talked about that in lecture chapter 25. You probably should know some of the characteristics of what makes up the eye, including the cornea, the lens, the retina, and characteristics of that. Okay, so a little bit on just what the parts of the eye are, particularly if you're a biology major and such. So that's all we're going to do there. Okay. All right. Um, 25.4 telescopes. And the fact that the magnification is based on the focal length of the object over the focal length of the eyepiece. So whether it's a mirror or a lens, and the eyepiece is what you see through, and the magnification is based on that. So a little bit on those characteristics. All right, what's the difference between a reflecting telescope, refracting telescope? All right, 25.6. is on aberration. And this would include spherical, chromatic, and then also also a little bit on astigmatism. This is the characteristics of lenses, but as far as people are concerned, astigmatism, how does that work? So what are the characteristics of these two? And then the last section, the last section is on 25.7, is on limits of resolution. And this deals with the fact that if we have a real mirror, real thing, like a mirror, your eye, it has a width D to it, capital D, then theta, right, how far something is away. If this is a distance S, it's a separation distance, like two lights. This is L. Then theta, which is in radians, which is approximately S over L, is 1.22 lambda over D, where this is the distance to whatever it is the two sources are to separate, to keep them distinct. This is the image, this is the object, whether it's a telescope, eye, your pupil, your eye. Lambda is the wavelength you're trying to see in, whether it's visible light or for a telescope, different types of light, X-rays, radio waves, and just 1.22 is the factor. So that's that part there. And that's the limit where you can actually resolve these two. So this is the limit into two actual objects and not just blurred into one. So that is, yes, the rest of the chapter 25. So that's what we have for